Okay, so today, or this week, or today's lecture, we'll take a look at correlation and linear regression. This is chapter 4 in our textbook, and this chapter falls still under the category of descriptive statistics. So last week, we covered chapters 1 through 3, and those were all about being able to describe some data. Okay, and chapter 2 was, we described things visually. We created histograms for numeric data and dot plots, and also, for categorical data, we had bar charts and so on and so forth. And then in chapter 3, we learned numeric summaries, being able to describe a set of numbers using a few values like the mean or the median, the values to describe the spread like this standard deviation and the IQR and things like that. And what we will be doing today is we will now look at describing relationships or associations between numeric variables. And in particular, we'll look at the correlation and linear regression as a way to kind of describe that, okay? And so, this is what this slide basically says. Chapters 2 and 3 were about describing the data. And in chapter 4, we're also describing data, but we're describing relationships between variables. So the idea here, when we want to describe relationships between variables, is that we go out, we collect data, and each observation or each kind of individual that we study, we might ask more than just one question, okay? So it could just be one question. I think one of the examples was, how many goals did this soccer player score? And we created histograms based on the number of goals that they scored, okay? Or, I don't know, what other variable we might be looking at. What was the weight of the baby when it was born, or something like that, right? What was the weight of the full-term baby? But if you think about that data set, that births data set that had the weight of full-term babies, there might be other variables included, right? Some of those variables are categorical, such as, did the mother smoke, yes or not? And others might be numeric, such as the years of education that the mother received, or I think one of the variables is like how much weight did they gain, or something like that. Okay, and so what we want to do is we want to be able to take a look at two of those variables, and in this case they have to be numeric variables. And we want to see if there's any kind of association or relationship between them. So, for example, let's say we were looking at houses in a certain neighborhood, and there's a bunch of different variables that we can measure. We could record how many bedrooms does the house have, how many bathrooms does the house have, how many parking spaces does the house have, or like garage spaces, okay? But we could also ask, but probably a common measure is how many square feet, okay, what is the size of the house? And then another one is, what is the cost of the house, right? And so we're going to look at two variables, the size of the house and its value, all right? And so both of these things are numeric. You write them down with numbers, and it makes sense to compare the numbers and say this one has a higher square footage than the other, therefore it's a bigger house. This one has a higher cost, therefore it's more expensive. And overall, you see a general trend, okay? That houses with more square feet will cost more. Houses with fewer square feet will cost less, okay? Now, of course, there's always going to be exceptions to this. You can have a house that's very big and costs little because maybe it's falling apart. Maybe you have a small house that costs a lot because it's, it's fancy or something. Especially if you're just looking within one neighborhood, right? Or, if Again, if you go to different neighborhoods, now things will be quite different, right, in price. But basically, what we want to look at today is quantifying the relationship, okay? Rather than just saying something generic like bigger houses mean higher cost, we want to specify values and specify this relationship and say, if one house is 1 square foot larger than the other house, we estimate its cost to be $350 higher, okay? Or if another square house is 100 square feet bigger, we expect it to cost, according to this, $35,000 more than the other house, or something like that, okay? We want to be able to quantify and not just say bigger houses cost more, smaller houses cost less, but we want to be able to specify exactly what we mean. So how do we figure that out, okay? That's going to be the focus of today's chapter. All right, so we'll take a look at a data set here, okay? This data comes from the U.S. Census Bureau, and it tracks age of first marriage over time. And in this data set, there are 3 variables: the year in which the data was recorded, and during that year, what was the average age of men's first marriage, and what was the average age of women's first marriage. So they kind of look at basically all of kind of the marriage licenses or certificates that were filed, and we looked at people who were getting married for the first time, and we looked at the average age, okay? And it doesn't necessarily have to be that this man married this woman, okay? It could have been a same-sex marriage, and it was just at this time, these were the people who got married for the first time this year, and if it was these were the people who this year got married for the first time, and what was their average age? All right, so it's not saying that this person married this person or anything like that. Okay, and the data set, just looked at men and women, and I understand that it wasn't very inclusive to include people who didn't identify as men or women, but this is our data set here, okay? And this is what it said. In the year 2019, people who got married for the first time, their average age for men was around 29.8 years, and for women was 28.0 years, okay? In the previous year, 2018, the average age was 29.8 for men, slightly lower for women, 27.8, so on and so forth, okay? And obviously, there are going to be people who were older when they got married for the first time, and there were people who are younger when they got married for the first time. And this data was tracked for across many years. Early on in like the 1900s, I think the earliest data set is 1890. And at that time, it was just recorded once every 10 years, okay? So in, say, 1930, average age of first marriage for men was 24.3 years, and for women was 21.3 years, okay? So there's a few things that we could plot. One is we could say, all right, what was the average age of men versus average age of women? Okay, so we could just take these 2 columns and plot them against each other, okay? And so each dot here is basically a different year in which data was recorded, right? And I don't know exactly which year this dot represents. I think this one is 2019, and some of these over here were like 1890 or whatever. So let's see, 1900, 25.9, 21.9. So 25.9 and 21.9, I think this is this dot right here. So that was the year 1900, okay? And each of these dots represent different years. And what we see the dots plotted, and it looks very much like, almost like a straight line, okay? There's a couple things that don't quite fit the straight line, but overall, in years where the average age of men's first marriage was high, that tended to correspond to years where the average age of women's first marriage was also high. And in years where men got married at a young age, that also tended to correspond to years when women got married at a young age, okay? So if a man got married at around 24 years, women got married at around 22 years that year. And something down here looks like 22 years for men and 20 years for women. Over here, around 30 years for men and 28 for women, and so on and so forth. Okay, and again, this is the average, so there would be people who are older or younger, and so on and so forth. And so I think these are the comments that summarize that up. Very strong relationship between men's average age of first marriage and women's average age of first marriage. In years where the average age of men's first marriage is high, women's average age of first marriage is also high. Correspondingly, when it's low, it's also low for the other gender. And if you look at it, there's consistently around a 2-year difference, right? If you go up to something around 28, corresponds to around 26. Over here for 24 corresponds to 22, 26 corresponds around 24, so on and so forth. Pretty strong relationship around 2-year difference here. Here, I'm creating a different scatter plot. And on the horizontal axis, on the x-axis, I put the year in which we recorded data. And on the y-axis, I'm putting the average age of first marriage. And here, this one is for men, and this one is for women. And what do we see? We see similar patterns, but also something quite different here, okay? So over back here, it was kind of like a straight line relationship. And here, we don't have a straight line. We have kind of a V, a V shape here, okay? And similarly over here. And what do we see? Around 1890, 1900, the average age of men's first marriage was around 26. And as time went on, the average age of first marriage went down until it reached kind of a low at around 1960. And around 1960, it seemed like average age of men's first marriage was around 22 years. Okay? So in 1960, by the time a man was 22, that was kind of the average age in which they got married. And women would be, in 1960, average age of first marriage was around 20. Around 20. So that, I think some of you are probably 20 already. Interestingly, for women in around 1890, 1900, the average age of first marriage was around 22. Okay, and again, it looks like it dropped maybe with a small increase during the 1940s, but consistently went down until we reached around 1960, which is also around the lowest for both. And then consistently after 1960, average age of first marriage just kind of steadily climbs year after year until for the next 60 years, from 1960 to 2020, down here, the lowest is at 22, climbing up to age 30 for men, and here around 20, climbing up to age 28 for women. And so we see kind of this this relationship here. And so we would say there's a very strong relationship, but we can't really define it with a single straight line. It appears from around 1890 to around 1960, the average age of first marriage, both for men and for women, decreased year over year, okay? And then from around 1960 to 2020, average age of first marriage continued to increase year after year, both for men and women, okay? So interesting relationship, but a straight line just doesn't, one straight line doesn't do it. If you kind of split the data at 1960, then yeah, a straight line kind of works. But, straight line on this half and a straight line on that half kind of works. But overall, one straight line for the entire relationship just doesn't work. So, again, with this chapter, what we want to do, one of our goals is being able to describe relationships between variables. And so there's a few things that we should mention, and that would be the shape, the trend or direction, the strength, along with any outliers. So the shape, as far as this class goes, we are going to either use, we'll just kind of categorize things as linear versus non-linear, okay? If you were to take more statistics courses in your future, you'll probably have more relationships, more names to describe these things. You can have an exponential and a quadratic and different kinds of things, but as far as we're concerned, we'll just have linear, meaning a straight line, single straight line works, and non-linear means is not described with a single straight line. So the examples, these are examples from the textbook. I guess we got data from some kind of search engine, and we looked at, I think, different weeks in the year or something, and we asked, did people search for vampire, and how many times did they search, or did people search for zombies? And apparently, in weeks in which vampire was searched frequently, zombies were also searched frequently, and in weeks where vampire was searched infrequently, zombie was also searched infrequently. So, I'm not quite sure. Maybe there's like seasonal or holiday trends related to that or something. Who knows, okay? But there's overall a straight line relationship, okay? This over here shows a different kind of relationship. And this one is the relationship between temperature and the amount of ozone. So ozone is, I guess, a form of oxygen. And we often think about the ozone layer, which protects us, but surface level ozone in kind of the air you breathe is actually not good for your health. It's good when it's high up and it's protecting us from radiation, but down here, not as great. And apparently there's a relationship between temperature and ozone, and it seems like when on days where the temperature is high, there's generally a higher amount of ozone, and on days where the temperature is low, there's less ozone. But that relationship should not be summarized with a single straight line, okay? And so we have a little bit of some curvature in this relationship, and we would say this is a nonlinear relationship. And basically that's how we would describe any of these types of things. Let's talk about trend and direction. So the direction of the relationship we can say is either positive, negative, or neither positive nor negative. Positive basically means big X, big Y, little x, little y. Negative means they kind of work opposite. Big X goes with little y, little x goes with big Y. Or I'm using large and small. Okay, large X goes with small y, small x goes with large y. And then neither positive nor negative just basically means that kind of general statements just don't really work. Large values of x aren't associated with large or small values of y. Small values of x aren't associated with large or small values of y, okay? So here is something, this is overall, there's a positive trend. Now there are a few outliers, but overall, there's a positive trend. The two variables here are the age of the car, so that's our x variable. How many years old is this car? And the y variable is how many miles, what's the mileage driven on the vehicle. And so what we see is, in general, cars that are newer have lower mileage driven on it. And as time goes by, as the age of the car gets older, when you get to a 10-year-old car, okay, you have more mileage driven on the vehicle. Now, there are some exceptions. Here it looks like a 6-year-old car with many miles driven on it. And here is like a 22-year-old car with comparatively not that many miles driven on it. But overall, there seems to be kind of this trend that as time goes on, mileage increases, and so we would say this is a positive trend. Large X, cars that are older tend to have large Y, more mileage driven on it. Small X, cars that are newer tend to have small Y, fewer miles driven on it. This is an example of a negative trend. Negative trend is large X is associated with smaller Y. Small x is associated with larger y, okay? And so this data set was looking at different countries. I think looking also at across different ranges of time as well. And so, this dot represents, say, a country. It could have been the United States in the year 2000, okay? And another dot could be, a different country, Argentina in the year 1970. And another dot could, I'm not quite sure, all right? So we've got a whole bunch of these different dots representing different countries. And the two variables, and this is an interesting trend that appears in the data, is that countries that have higher literacy rates, okay, a larger portion of the country can read, tended to have fewer total births per woman, okay? And countries with lower literacy rate tended to have higher total births per woman. So that's kind of how we measure, I guess, fertility, is we say, all right, well, how many babies were born and how many women in the population, and so on and so forth. And so this represents a country where, on average, women had somewhere between 7 and 8 children, okay, 7 to 8 births per children. And in that country, the literacy rate was around something under 20%, okay? And over here, this is a country where the literacy rate was somewhere between 40 and 50%, but also had somewhere around between 7 and 8 births per woman. Here's another country with a literacy rate of around 50%, but its total birth rate per woman was around 3. And over here, we have a lot of countries with close to 100% literacy rate, and in here, these tend to have total births per woman of around 2, a little bit less than 2, a little bit more than 2. Okay, there's quite a high concentration of countries there. So overall, we see a negative trend. Larger values of X tend to go with smaller values of Y. Smaller values of X tend to go with larger values of Y. Now, when you see trends like this, there's a tendency to want to draw some kind of cause and effect conclusion. And we might want to say, okay, increasing the literacy rate tends to decrease the total births per woman. But we have to be careful, and we don't want to say that the literacy rate is what is causing a change in fertility or something like that, okay? Or the vice versa, you don't want to jump to the other conclusion and say changes in kind of this fertility rate in terms of total births per woman is causing changes in literacy or something, right? What is happening, I'm not 100% sure. There's probably a lot of kind of complex social factors going on here, and economic factors playing into how many children a person or a couple or people decide to have, and the literacy rate and things like that. So there could be other confounding variables responsible for this, but it is certainly interesting to find, some kind of relationship between these variables. All right, over here is an example of a relationship that is neither positive nor negative. Okay, and these were apparently Forest City. I don't know where that is. They had a marathon, and they had a bunch of contestants and people participate, and they just recorded how long it took them to complete the marathon. And they asked, hey, is there a relationship between the time it took to complete along with the year of the person participating? And what we see is that in this data set, there isn't a very strong relationship. We have people who are young, 18, 19, 20, and some of them had fast completion times, around 3 hours, and some took longer, some closer to 5 hours. Okay, around age 40, we have people with quick race times and people with slower race times. And age 50, quick race times, slower race times. Age 60, quicker and slower. And there doesn't seem to be any kind of trend where we could say older people tended to take longer or less time, or younger people tended to take longer or less time. Just overall, yeah, you had old people and young people in your participate. You have people who completed it quickly and completed it in less time, and there's not a strong relationship. We can't say it is positive or negative here. So we would just say neither positive nor negative here. It doesn't always have to be a blob like this. Here's an example where we would also say there is neither a positive nor a negative relationship. Whereas over here, I would just say there's not really a relationship between these two variables. Over here, there is definitely a relationship. It's just that this relationship we can't use a single word like positive relationship or negative relationship here. There's certainly a relationship between x and y. When x is 0, y tends to be between 0 and 20. When x is 10, y tends to be around, looks like 100. When x is negative 10, y tends to be around 100. So there's definitely some kind of relationship. It's just to describe the overall relationship as positive or negative would be a mistake. And to try to use a single straight line would also be a mistake. The words positive and negative really mostly apply when overall, a straight line kind of does the trick. It doesn't have to be exactly a straight line if you're just using the words positive or negative. But here, certainly it is not linear and it is not entirely positive or negative. Okay? Now, if you split the data at 0, on the right-hand side, we would say there's a positive relationship. As x gets bigger, y gets bigger. And on the left-hand side, there's a negative relationship. As x gets smaller or lower, y tends to get larger. All right, so that covers the direction of a relationship. Let me go ahead and give you your first view quiz answer for today, and that is the letter D. D as in dog. D as in dog is your first view quiz answer for today. D. D as in dog. All right, we can talk about the strength of a relationship. The strength of a relationship between two numeric variables summarize kind of how much scatter appears in the scatter plot. We can also kind of think of this as, how well can you predict one variable based on the other? And so, talking about strength, you can say the relationship overall is weak or the relationship overall is strong. And those words kind of describe that. So here are two examples of relationships. Both of them have positive trends, okay? We see as x gets larger, y tends to get larger. As x gets smaller, y tends to get smaller. Same thing, x bigger over here, y bigger, x small, y small. So overall, the relationship is positive. But we would say the one on the right has a stronger relationship. There's less scatter. The one on the left has a weaker relationship. There's kind of more scatter. And the idea is, if we gave you a value of 30, how well do you expect your prediction for y to be? Okay, if we gave you some number, how precise can you expect your prediction to be? So here we're looking at, is there a relationship between someone's height and how much they weigh, and someone's waist size and how much they weigh. So we're measuring the y variable in both of these cases is someone's weight. The x variable is their height. So we have people who are 5 feet tall, 60 inches tall, and the people in our data set weighed anywhere, looks like 95 pounds to around 160 pounds. Over here we have people who are 75 inches tall, and 75 looks to be somewhere between 160 to 240 pounds. Okay, and I guess this is what, 77, 78 inches tall, and so on and so forth. And so overall, as people get taller people tend to weigh more, shorter people tend to weigh less. That's the overall trend. This is another, not their height, but now their waist size. So we say, I guess, what is, you take a tape measure, put it around their waist. What is your waist size in inches? And this seems to be a better predictor, I guess, So if you wanted to guess someone's weight, it is more informative to know their waist size than to know their height, okay? So people with larger waists tend to weigh more, people with smaller waists tend to weigh less, okay? And so we would say the one on the right is a stronger relationship than the one on the left. If you know the waist size, our prediction is likely to be more accurate than our prediction if we only knew someone's height. All right, so let's put all of this together and try to describe a relationship. So here we'll go back to our marriage age data set. And we're asking, is there a relationship between men's age of first marriage and women's age of first marriage? And the answer is yeah. There is a positive trend. The trend is linear. Years where men married at an older age tend to be years where women married at an older age. And the association is strong because if you look at how much scatter is there in the points, there's not a ton of scatter. It seems like they fit a straight line quite closely. Now, when we describe a relationship, we want to be careful, and we always want to use words like tends to or things like that. Just because whenever we talk about individuals or just any of these individual points, there's going to be variation. And so overall, large x tends to go with large y, and overall, small x tends to go with small y. That's fine. You can say there's a positive relationship. But of course, there's going to be exceptions. Okay, there's going to be some exceptions. And there's, back here we had a vehicle that was old with relatively few miles on it. Here we had a vehicle that was relatively not old, but had many miles driven on it. So overall, there's a trend, but it's not going to be true for all individuals. And so if there are any outliers, anything that's unusual or any outliers there, it's a good idea to point them out. It's a good idea. All right, so let's introduce correlation. So we've been describing relationships between numeric variables, and we have kind of this vocabulary built up: linear, nonlinear, and positive or negative, and strong and weak, and things like that. Now we want to quantify it, okay? So, just like when we introduced the standard deviation is a value that we can use to quantify the amount of spread. We can say in the second grade classroom, there's very little spread in the ages. In the DMV waiting room, there is a lot of spread in the ages, okay? But rather than just saying little and lots, we can give an actual number. We can calculate it, and we can say the second grade classroom has a standard deviation of 0.6 years. The DMV waiting room has a standard deviation of 15.4 years or something like that, okay? And we can kind of put a number to quantify what we mean by a little, what we mean by a lot. Correlation coefficient, correlation is similar. It is just a number that lets us quantify the relationship. Rather than just saying the relationship is strong and the relationship is weak, we can give it an actual number. So the correlation is a number between -1 and +1. The symbol we use for it is the letter R. Okay, R like relationship. Okay, it's always between -1 and +1, and it tells you the strength and the direction. So if the sign of R is the direction, if R is positive, the direction is positive. If R is negative, the direction is negative. And if R is 0, it is neither positive nor negative. Values that are close to 1 or close to -1 indicate a strong linear relationship. Values that are close to 0 indicate a weak linear relationship. Keywords here being linear. So correlation really only makes sense for linear relationships. Okay? So this has a correlation of 1. Okay? If you have a correlation of 1 or -1, you have a perfectly linear relationship. In this case, it is positive and it's perfectly linear, and so we have a correlation of +1. Here it is height in inches versus height in centimeters. If somebody gives you their height in inches, can you predict their height in centimeters? And the answer is yeah, you can predict it and you can know it exactly what it is, because it's just a simple conversion factor. You just multiply the number of inches by a number, 2.54, and that's going to be how many centimeters tall they are. So there should be no variation here. Here are examples of linear relationships overall, and we can see that as R increases, the strength goes up, whereas R decreases, the strength of the relationship goes down, that there becomes more scatter. So here, if we revisit the height and the weight, there's some scatter. Overall positive relationship, we have R around 0.72. More scatter, R is around 0.48. And here, lots of scatter, maybe still slightly positive relationship overall, R of 0.19. Okay, so as you have different quantities for the correlation, the amount of scatter changes. You can calculate the correlation. Generally, we just use the computer to calculate the correlation. There is a formula, but we're not going to cover how to calculate the correlation by hand. Okay? So normally we just ask the computer, calculate the correlation for us. And on R, you just type in core, C-O-R, for correlation. You give it basically your column for one variable and your column for the other variable. So here we're going to go to the marriage data set, ask for the column men. We'll look at marriage data set, ask for the column women. What's the correlation there? We get a correlation of 0.985, which is very close to 1, indicating we have a very strong correlation. And again, here's the data set where that's a very strong correlation, and it's reflected here. Okay, it's something very close to 1, 0.985. Okay. I guess if you wanted to, you would convert all of your x and y values to z-scores, and then you multiply them together, and then you add them all up, and then you divide by n minus 1. That's how you get your correlation, but not a big deal. Okay. These are some of the rules or some properties of the correlation, and that is if you change the order of your variables, it doesn't change R. So what is the correlation between height and weight? 0.72. What's the correlation between weight and height? Also 0.72. Okay? So changing the order of the variables does not change R. Adding a constant or multiplying by a positive constant does not affect correlation either. And basically, this comes down to if you change your units, that does not affect correlation. So if you measured someone's height in inches and their weight in pounds, and then you decided to convert from inches to centimeters or pounds to kilograms or some other combination, the correlation is going to stay the same. Okay, converting units from one to another does not affect correlation. Temperature, going from Celsius to Fahrenheit, which involves adding a constant and multiplying by a positive constant, that also does not affect correlation. So you can switch from Kelvin to Celsius to Fahrenheit. It's fine. Okay. Correlation itself is unitless. And this one's super important. R using correlation only is useful for a linear relationship. Linear relationship only, okay? Now, the calculation of the correlation, it's just the result of a formula. So you can plug in numbers from a nonlinear relationship and it will still spit out a number for correlation. It's not meaningful. Okay, it's not meaningful. If you do this thing for a nonlinear relationship, you'll get a number. It's not going to be useful. Okay, so a correlation of 0 doesn't mean that there's no association, but it just means that there's no linear association. So if I go back to this slide and I calculate the correlation here, the correlation here is 0. Correlation here is 0. Does that mean there's no relationship between x and y? Now, there is a relationship between x and y. It's just that this relationship is not linear, and the relationship is neither positive nor negative. So you're going to have a correlation that is 0, but it doesn't mean that there's no relationship. Okay? And conversely, if you have a correlation of, I didn't put this in the notes here, but if you have a correlation of 0.9, that doesn't mean your relationship is linear either. You could have a nonlinear relationship, something like this, and if you calculate the correlation, you might get something like 0.9. Okay, you might get a correlation, I don't know if this can even be seen, but you might get a correlation of 0.9, but it doesn't necessarily mean that the relationship is linear. So you can't just look at the correlation and assume that the relationship is linear either, okay? So correlation of 0 doesn't mean that there's no relationship, it just means that there's not a linear one, at least. And then a correlation that's like 0.9 doesn't mean there's a linear relationship either, okay? The only time you can say you have a correlation that's linear is if you get R equal to exactly 1.0 or negative 1.0. So if you have R equal to exactly 1.0, that's only going to happen if you have a straight line, okay? But that in of itself is kind of uninteresting because it just means, really, it's just some kind of being multiplied by a constant, really. So anyway, last bullet point, I guess, is maybe I should make it bolder, but always graph your data first to make sure the association is linear. Okay, so we're going to take this and let's put it together, and we will talk about linear regression. So linear regression is the way we're going to quantify the relationships and create the equation of a straight line. Okay, so we're going to describe a linear relationship with the equation of a straight line, and it's useful if we wanted to make predictions, and it's also helpful in helping us understand the relationship between x and y. So if you think back to your algebra days, we said the equation of a straight line is y equals mx plus b, where m is the slope and b is the intercept. Okay? Same kind of idea here. We have a slope and an intercept, but we just use different letters. This time the slope is the letter B, the intercept is the letter A. And we're going to say y hat is equal to a plus bx. Y hat represents the prediction line, the equation of the line. The value we are predicting follows a straight line, or the predicted values follow a straight line, whereas the actual values in the data, y, don't necessarily follow that straight line. So when we do this, we got to talk about our x variable and our y variable. And depending on the textbook and depending on the problem or whatever, you might see different names for x and y. Okay? So other names that we might see for x are the explanatory variable, or the predictor variable, the input variable, the independent variable. Other names for y are things like the response variable, or the predicted variable, or the outcome variable, or the dependent variable. In all of these things, we're using x to make a prediction for y. We're putting x in, and we're getting y out. That's kind of the idea. Now, it doesn't mean, sometimes we're tempted to say x causes y, but that's not what's going on. All we're doing is we're just setting up some kind of thing where we're going to put in the x, we're going to get out the y. So we could say, hey, is there a relationship between height and weight? And we can, what we can do is we could set it up where we can say, okay, well, you give me the person's height, I'm going to predict their weight. In that case, height is the x, weight is the y. But somebody else could take that data and spin it around and say, if you give me someone's weight, I'm going to try to predict their height. Okay? In that case, weight will be the x. That's the value we're putting in, and we're trying to predict y, the height. Okay? And either of those things are equally valid and both make just about as much sense as the other, which is maybe not a ton of sense, but the idea of you take one to kind of make a prediction for other, right? Just like the thing with the cars. Tell me how old the car is. I'm going to try to predict what its mileage is. Okay, here's a car, 10 years old. Maybe it's got 130,000 miles. That's my prediction. Okay, a car that's 5 years old, I'm going to predict has what, 65,000 miles on it or something. Okay, whatever. I'm making stuff up. Okay, now you could also flip it around. You can say, all right, tell me the mileage of the car, and I'm going to try to predict how old it is or what year it was made. Okay? Okay, here's a car with 60,000 miles. Okay, we're going to predict maybe it's what, 4.5, 5 years old, something around there. All right? So whatever you're taking in is your x, whatever you're predicting is your y. And it's not that one is causing the other. It's just, that's how we're setting it up. Okay? All right, so here is, I guess here's another used car example. We got a bunch of these in the book, I guess. This time, we're going to take the age of the car. That's going to be our x variable. And we're going to try to predict how much it's worth, okay? Now, this is, I don't know when this data set came up. I think it's hard to find cars in this price range now. Okay, so we're going to say, all right, x is the age of the vehicle in years, y is going to be its value. And apparently, they gathered some data. And what we find is overall there's a negative relationship. Cars that are 15 years old tend to have lower values than cars that are 0 or 1 year old. Okay, so if you're going to buy a used car, maybe some of you are thinking about buying a used car, you've got options, right? You go online and you look. All right, here's a car, it's only 2 years old. It's probably going to cost more than the car that's 6 years old, right? And you just kind of got to factor in, my budget and stuff. All right, and so when we created this equation, the equation that we got was the predicted value is 21,375 minus 1215 times the age. So, so thus, if we plug in 12 years, all right, 21,375 minus 1215 times 12. 1215 times 12 is 14,580. And you plug it in, you plug in 12 years into age here, and you get 6,795. So we're going to say, all right, a 12-year-old vehicle, I guess that's a 2010, figure, some car, 10 years old, has a value of maybe 6,795. Okay, again, this is a made-up data set. I don't think these numbers are accurate at all. But this is kind of the idea, that if you just plug in the age of the vehicle, it spits out a number, and this is how much we predict how much the car is worth, okay? Now, again, this is just a prediction. The actual vehicle that's 12 years old could be worth a lot more or less than this, depending on a lot of other factors. Basically, the 12-year-old Mercedes-Benz is probably going to be worth more than your 12-year-old Honda Civic. We love Hondas, but as far as the values go, things like that happens, right? Oh, versus like I don't know, other brands as well. Okay, so here is a simple data set. Just let's try this out. Okay, this one I only have 6 people, and we have their weight and their height. Okay, we're going to use weight on the x-axis, height on the y-axis. Okay, so we're going to plug in someone's weight. Based on their weight, let's predict their height. Okay, and again, I just made up some data points, and I kept it small. So we have a person who weighs 104 pounds, and they're 5'1", and a person who weighs 110 pounds, and they are 5'2", and 170 pounds, and they're 5'6", and so on and so forth. These are just some made-up numbers here, okay? And this is kind of the plot of these 6 points here. And the question is, all right, how do I find the line? How do I find the line that's going to fit? How do I find the slope and the intercept? Okay, well, if you're using the computer, this can be done very quickly. All right, so in R, you just say, all right, create a model, LM. LM stands for linear model. And you do height tilde weight. You say predict height based on weight. You specify your data frame, okay, with a table in which this data is stored. And it comes back and it says your intercept is 52.397 and your weight is 0.08595. I didn't do this in Excel, but let's be honest here. After this class, I don't know how many of you are going to use R. I love R. And I think R is really great, and I stand by its use as far as this class goes. But, maybe more realistically, if you go somewhere. All right, let's do weight, height. Let me just type in these numbers. 104, 61, 110, 62, 141, 63, 125, 64, 170, 66, and 160, 68. Okay, so I've got my 6 data points in there, and just in a little Excel table, and I'm going to highlight that, and I'm going to click Insert, Chart. Okay, and we will do a scatter plot right here. Okay, so here is the plot. So that looks a lot like this, just maybe kind of stretched or compressed a little bit. All right, and then you have some options here. Let's do the trend line. Okay, I put in the trend line here, and then over here, we'll do linear. That's what we want. More options, and what we also want to do is we want to say display the equation. Maybe display the R² value, okay? So again, the way we did this, just to show you, once again, if you wanted to do this in Excel, don't do Excel for your lab, okay? For your lab, you got to use R. But outside of this class if you wanted to do something like this. You would enter your data, insert, go to charts, insert a scatter plot, and then under your options on this little plus element, chart elements, you want the trend line, and under more options for the trend line, you can scroll down and you can say, I want the equation, I want the r squared value or r or whatever. Okay, and these are kind of the values that it spits out. All right, so what do we see? We get 0.0859x, that is our slope, which is exactly what r spits out, 0.0859. Oh, I guess they keep in an extra decimal place, 0.08595. Okay, and then the intercept, 52.39726. 52.397 is what r tells us. Okay, so this is there you go. All right, so in Excel, in R, you get kind of the same idea here. And basically, we're saying y, height, the value we're predicting, is going to be 52.397 plus 0.08595 times the weight. Let me give you, I've only given you one view quiz, right? So let me give you your second view quiz. Second view quiz answer today is the letter C. C as in cat. C as in cat is your second view quiz answer. I think I have to get a mic. My voice gets tired. Okay, so this is how you would do it in R. You know, I could just do this really quickly on R as well. So in R, you would create your data set. Okay, so you'd create a little, you'd create your vectors as such. 61, 62, 63, 64, 66, and 68. And what do we have? 104, 110, 141, 125, 170, 160, and then I'm going to create a data frame, data.frame. We'll put the two variables together. So there's our data set right there. And then if I wanted to create a model based on this, I would just type in LM for linear model. We want to predict the height based on the weight. Our data comes from the data set DAT there. And what does our model look like? Here it is. There's your intercept and there is your slope. Okay, you can plot this, all right? And this is what the trend line looks like, okay? Plot of weight versus height, and you could do AB line. AB line is adding this line, AB kind of, the AB being the, whoops. Back here we said, where'd it go? Y hat is equal to A plus BX. That's kind of where why it's called an AB line. A being the intercept and B being the slope. So we wanted to add this AB line, intercept slope line, and that's kind of where we are going with this. And that's what it looks like. And it looks just like this, just kind of, here, let me see if I can, axes, what are my axes? More options. How do I change this thing so the minimum is not 0 but 100? Let's see. Axes. No, we want them. Options. Text options. Axis options. Bounds. Oh, okay. 0 to 180. Okay, so let me just change this to 100. All right, so that looks a lot more like what we have here. Okay, 100 to, you know, it looks Just about right. Okay. So anyway, so that's what you have, right? R kind of automatically fits the axes to your data, and Excel uses different rules for however it goes. And there you go. All right. So that's that. And usually when you do correlation and linear regression and stuff, especially because your data set's often quite big, you would just have the computer find it, right? So you can have R find the correlation line for you, and if you wanted to do it on Excel, Excel is capable of doing this as well. But we will also show you how to get the correlation line, the linear regression line, the slope and the intercept, based on kind of do it yourself, right? And to do this, you need these different values. You need the mean of your x, your standard deviation of x, the mean of y, and the standard deviation of y. And you would need the correlation between x and y itself. So again, correlation, we did not cover how to do correlation by hand, so you'll just have to accept that the computer will calculate the correlation for you. But if you have these things, you could calculate the mean of x yourself. You could calculate the standard deviation of x yourself. And even though the standard deviation calculation can be a little bit tedious, depending on how many values you have, you could do it, okay? So on the computer with R, you learned how to calculate the mean and standard deviation, right? We did this in our lab. So you just type in mean, and you give it the name of the vector. So you can say, what's the mean of weight? Mean weight is 135. What's the standard deviation of the weight? And you get 26.7826, okay? And what's the mean height? 64. What's the standard deviation of height? 2.607. And what's the correlation between weight and height? Or height and weight? The order doesn't matter. Here I did height comma weight, and we got 0.88. Here I did weight comma height, and I get 0.88. So these are the 5 numbers that you need to do to get this. If you wanted to, you can get the average. You can say, what's the average? That's the mean. And you would highlight your column here. So the average weight is 135 equals average, and you do for height 64. And you do standard deviation. Okay, so, in Excel, it's standard deviation S. All right, and we get 26.7283. We see this, and I can just copy that over, and I get 2.60768. So these are the standard deviations. So this is the mean, this is the standard deviation, and then the correlation, you do Correl, okay, equals Correl, and you highlight this column, and you highlight that column, and we'll get the same numbers, 0.88093. Okay, so these numbers, same numbers that we get here, you can do it in Excel as well. All right, well, anyway, once you get those numbers, it's just a matter of plugging them into this formula, okay? Your formula for the slope is the correlation, 0.8809 times the standard deviation of y divided by the standard deviation of x. So 0.8809 times 0.2607681, which is what we have here, divided by the standard deviation of the weight of x, 26.72826. So I plug that in. I get 0.08595, which is exactly the slope that was output by the computer, 0.08595. All right, that's how you get the slope. And then once you get the slope, you punch that in to get your intercept. So you have to find your slope first. Your intercept is going to be mean of y bar, 64, again from the previous slide, minus b times x bar. X bar was 135. So we plug that in, we get 52.397. Your quizzes and stuff, they're open note. I would say put a star on this page of notes because you'll need these formulas for your next quiz and so on and so forth, okay? So, or just write these formulas down on another piece of paper that just says easy to remember and find. Because on the quiz, you know, you don't want to be flipping through, I don't know, I've got 60 slides for each of these lectures. So anyway, this is an important slide for these formulas here. Just plug in the numbers, and these are what you get for your slope and your intercept. Okay. And so you put those two together. The intercept is your A, your slope is your B, and your predicted is going to be, y hat. Your predicted height is A plus B times X. Our X is the weight, our Y is the height. So we get 52.397 plus 0.08595 times the weight, which is exactly what we have. And we say, all right, let's predict someone's height if we know that their weight is 170 pounds. Okay, so we plug in 170, we multiply it by 0.08595, we add on 52.397, we get 67. Okay, so that's what we predict. If someone's 170 pounds, we predict they're going to weigh 67 pounds, or they're 67 inches tall. If they weigh 170 pounds, we predict they're 67 inches tall. When we look at our data set, there is somebody who weighs 170 pounds, and their height is 66 inches tall. Okay, so that just means our prediction is not the same as what the actual value is. And the difference between the prediction and the actual value, that's known as our residual. The residual is the difference between what the actual value is and what the predicted value is. And basically, you know, I just said, hey, here's the line. There's actually a lot of math involved that I kind of skipped over. But by using these equations for the slope and the intercept, this is going to give you the line that minimizes the squares of the residuals. And I'll illustrate what that means. But basically, we could have drawn any kind of line here, right? So this is the line that we have, but you know, what would have happened if I had if I could reach, you know, what if the line was steeper or more shallow, okay? All right? How would those lines have worked, okay? Well, you wouldn't have as good performance as far as the residuals go, okay? Residuals are the difference between the actual value, this actual dot, and the line. So here we have a very small residual. This dot is very close to the line, and so we have pretty good performance. Over here, we have a little bit of a residual. We have about a residual of size 1. The actual value was 66. The predicted value was 67. There's a difference of about 1 unit here, okay? This one, we've got a residual of around 2. The actual value is 68. We're predicting something around 66. So we have a residual of around 2. Over here, we have residuals that are pretty small, like 0.1 or 0.05 or something, you know? And the idea is, well, you've got a whole bunch of these points, and we want the overall, the smallest amount of residuals, okay? And technically, it's the smallest amount of squared residuals. So the line that we pick will minimize the sum of the squares of the residuals. And I've got maybe a little illustration to show you kind of what's going on there. So no other straight line that we have will produce predictions with less total squared error. Okay. Another property of this regression line is that it always passes through this point, x bar comma y bar. It always passes through the mean x and the mean y, meaning if you have an observation with an average x value, then your prediction is going to be average y. So if someone is average x, we're predicting their y is also average. And that kind of makes sense. That makes sense. Okay, let me show you this this visualization, the idea of least squares regression. Okay? So here, we have 1, 2, 3, 4, 5, 6, 7 data points. And I guess we're predicting, I don't know, this is our x and this is our y. And what I can do is I can adjust the slope and I can adjust the intercept. Okay? Right now my intercept is 0, and we could say, well, what? Right now we have an intercept of 0 and a slope of 1. What would happen if I change my intercept? What I can do, that changes the, so just pay attention to the red line. Ignore these boxes for now. I'll explain in just a moment. But you can see as I increase the intercept, the line slides higher, right? And as I decrease this, the line slides lower, okay? So here it is at 0. I can bump this up. And now we have an intercept of around 10, 9.58, I guess. Or I could bring it down and the intercept goes lower. Okay? So here we can adjust where the red line goes. And I can also change the slope. Right now we have a slope of 1, but I could decrease the slope. Okay? And that makes the line shallower. Okay, I can also increase the slope, and that makes the line steeper. All right. So I have these two dials to. It's like an Etch-a-Sketch, except one is where you're going up and down, and the other is not horizontal, but how much angle you have. All right. So these are kind of the two knobs that I have. I can adjust where the line intercepts by kind of increasing or decreasing my intercept. I can adjust how steep my line is. Okay, so those are the two knobs that I have, and the goal is to find the line that minimizes the squares of the residuals. So the residual is, again, the difference between the actual value, these dots here, the pink and the brown and all of these dots, and where the line is. So let's just look at this pink dot here, okay? I can try to increase my intercept so that the dot is right on the line. And if I do that, now I have no pink residual because the actual value is on the predicted value, so I have no difference between the actual and the predicted. I have no residual there. The unfortunate thing is by pulling the line up to pink, what has happened? Now this line is very far away from the blue dot, okay? The blue dot is now far away from the line, and so I have a big residual there, okay? So the way we're calculating the performance of the line is we take each of these, all of the residuals, we square all of them, and we're trying to minimize the total squares of the residuals. So we have to take into account all of the data points, all of the residuals, all of the squares. And so we say, okay, well, if I'm over here, maybe my performance isn't that great. So should I lower the line and here's somewhere in between, and maybe that's a good median. Okay, we can say, okay, well, what if I made the line steeper? Would that improve? And you can see, I'm not quite sure what the best line is, all right? And you can say, all right, well, maybe we need to, all right? And so the goal is, all right, by kind of adjusting both of these knobs, all right, making a line that's a little bit steeper, a little bit shallower, what is the line that's going to minimize the total squares of the residuals, right? So I could try to adjust the line so we have very little residuals over here, but now I've increased the residuals over here, and I can try to adjust where the slope is and where the intercept is, and the goal is to get something. All right, I don't know what the total squares, which line has the best, okay? But that's what this when you use these formulas to calculate the slope and the intercept, it will result in the line that minimizes the total sum of the squares of the residuals. Okay, so visually, does that kind of make sense? Where we've got residuals, the difference between the actual value and the predicted line, and you can move that line around, but when you move it around, you probably will end up increasing the size of the residuals to other points or decreasing the size of the residuals for other points. And overall, you have to take into account all of the data points, and you want to find the one that minimizes the total sum of squares for all of the data points. And that's what that regression line will do. Okay, the one that has this slope and this intercept is going to be the line that minimizes that. And that was found, via some calculus and math that we're going to skip over. You just have to kind of take my word for it. If you do like major in statistics, or you take a mathematical statistics course, you will prove this result. But for now, you'll just have to take my word for it. Okay. So how do we interpret this? Once we have the slope and the intercept, we can try to make meaning from it. The slope tells us how much our prediction for y changes based on x. If we bumped up x by 1, how much does our prediction for y goes? Okay. So when we looked at this example for height and weight, our slope was 0.08595. So we'll just call it 0.086. 0.086. Okay. The y is measured in inches. X is measured in pounds. And basically, we're going to say if the x goes up 1, our prediction for y goes up 0.086 inches. Okay. If x goes up 1 pound, y goes up 0.086. Now, you have to be careful. When we say x goes up by 1, we're not forcing x to increase by 1. We're not saying we fed this person more food and they gained a pound of weight. Okay? We're not forcing someone to gain weight and causing them to grow taller. Okay? All we're saying is that if one person weighs 100 pounds, maybe we predict their height to be 61 inches. I'm just making this up. Okay? And if there's another person who weighs 101 pounds, okay, then knowing nothing else about this person, right? All we know is this person weighs 100 pounds, this person weighs 101 pounds. We don't know anything else. If we had to predict this person's height, we predict them to be 61 inches. And if we're predicting this person to be 61 inches, the person who weighs 1 pound more, we're predicting is going to be 61.086 inches. Just the amount of the slope, 0.086 inches taller. Now, it probably doesn't make sense to compare 100 versus 101 pounds, but maybe 100 versus 110 pounds. So if we have, on average, if someone weighs 100 pounds, maybe we're predicting them to be 61 inches tall. On average, if somebody weighs 110 pounds, we're going to predict them to be 0.86 inches taller, 61.86 inches, almost 62 inches tall, so on and so forth. Okay. So the slope is how much your prediction changes if x goes up by 1. Again, you can't force somebody's x to change, and a lot of times that's not even possible. Like if we flip this around and we said, all right, predict someone's weight based on their height, you can't just take somebody and just stretch them out and say, okay, your x has gone up by a value, okay? There's not like this cause and effect type of thing where you can just control someone's x. Here is another example. We revisit the used car prices. And here we're saying, okay, the slope is negative 1215. Negative 1215. The x variable is the age, measured in years. Value is dollars. So if the car, if the age of a car goes up 1, our prediction goes down 1215. So if we have a 5-year-old car and if we predict it to be 15,300, then another car that's 1 year older, 6 years old, we would predict to be 1,215 less, so around 14,085. And that's what this slope means. So it's how much your y changes, how much your prediction for y changes if x goes up by 1. The intercept sometimes has an interpretation, and that is, what is your prediction for y if x is 0? Now, sometimes it makes sense for x to be 0, and other times it's nonsense to plug in 0 for x. So for the car, can you have a car where the age is 0? Sure, that would be a new car. And according to this line, we would say we predict its value to be 21,375. The intercept is 21,375. That's what we predict the value to be if x is 0. Okay. Over here, we're predicting someone's height based on their weight. You cannot have a person with a weight of 0. Weight of 0 is literally no person. So you can't, there's not a meaningful interpretation here for the intercept. Okay, it does not make sense to plug in 0 for x. So this intercept is kind of meaningless. Okay, we have a bunch of warnings now. And so linear regression is very useful. And here in this class we're covering simple linear regression. But if you were to say study statistics or something, you can take an entire course on linear regression and basically just expand this. And it's one of the most powerful and useful tools that we have. But because it's so useful and because it's so easy to kind of create models in, say, Excel or wherever, right? There's lots of tools that employ linear regression. It's also frequently misused, okay? So number one, don't try to use a linear relationship to describe nonlinear relationships, right? So always create a scatter plot. Always ask yourself, does it look like a straight line is reasonable? Is it reasonable to use a straight line here? And if so, go ahead and use linear regression. If not, stay away. Also, if there's any outliers, outliers can have a big effect on the correlation, have a big effect on R. Always check the scatter plot first, okay? This is what we call Anscombe's Quartet. This is, you can look this up on Wikipedia as well. I think this is where I took this picture. These are 4 different data sets. And if you look at only the summary statistics, if you look at what's the mean of x, what's the mean of y, what's the standard deviation of x, what's the standard deviation of y, what's the correlation between x and y, what's the linear regression line, all of these, all 4 data sets have the same values. It's hard to believe, but all 4 data sets, if you look at the mean x, they're all exactly the same. If you look at the mean of y, it's all exactly the same. And you ask, what's the correlation between x and y? They're all exactly the same. What's the standard deviation? And so this was, it feels kind of strange, but yes, this is what happens. Now, and so they all have the same linear regression equation. Does it make sense to use linear regression in all of these situations? And I would say the only one where it makes sense to use linear regression is this first one. Okay, this first one, sure, it makes sense to use a straight line equation, linear, to calculate linear regression and use this line as a prediction line. But if you look at this one, but when you look at the plot, you go, oh yeah, that's not a straight line. That looks like the start of a parabola or something like that. It doesn't make sense to use a straight line equation, right? If you had to predict what is y going to be at 16 and 18, just visually, you would not use this straight line over here. You would say, okay, if x is 16, y is going to be lower, maybe around 6, right? Maybe around 7. You would just kind of eyeball it, something like that, right? You would not use this. The blue line says if x is 16, we would predict 11 or 10 point something. And you'd say, no, that doesn't make sense. What about this one? If you had to use the line and predict 16, would you use the blue line? No, you'd probably say, I'd predict 16 to be something around here. Just 9, 8 point something, a little bit higher than this next dot. What's going on here? Okay, we've got this one dot that's an outlier, doesn't fit the trend of everything else. And this one dot is throwing off your prediction line. what is this dot doing here? I don't know. This could be a typo. This could be something went wrong in the measurement system, right? You know, you were measuring somebody, you're measuring people's weights or something, and this person forgot to take off their shoes. I don't know, okay? Or take off their, you know, heavy helmets or something, right? Something went wrong, and something's not being measured correctly. This seems, or maybe this is a real thing. I don't know. You should investigate. Why is this dot so far different from everybody else? This one, what's going on here? If you covered up this one dot out here, you realize, oh, you only have x measured at one location, basically, okay? Pretty much everyone in the data set has an x of around 8. And so you get people with large y and small y, but they all have x at one value. And then you get one person whose x is different from everyone else. And that person's y is over here. And now we're establishing a trend based on this one thing. It would be kind of like, let's say we asked everybody, okay, what is your income and how many fingers do you have, all right? And let's just say everybody says, I've got 10 fingers, and we have some people with high income, some people with low income, okay? And we say, oh, is there any kind of relationship between fingers, number of fingers, and income? And based on that, well, everybody has 10 fingers, so it doesn't really quite make sense, okay? Now, let's say we encountered, somewhere in our data set, we encountered somebody with 11 fingers. They have an extra finger, and that person happens to, you know, make millions of dollars, right? And we say, all right, let's establish a trend here, okay? And now it would look like, oh, having one additional finger suddenly increases your income or something like that, right? And we would say, that's silly, that's silly. But that's basically what's going on here. We're using one x value that's different. This one person that's different from everybody else, we're now using to establish this entire trend. And that's what's happening in this data set. And I think when I explain it and kind of say, yeah, if it's like trying to say, you know, establishing a relationship between the number of fingers somebody has and their income, that would be kind of a silly thing to do. You know, this kind of stuff happens in business and things like that, where they just say, oh, we got this one observation and now we're establishing an entire trend, right? Depending on, you know, surveys or demographics or things like that, right? If your survey quality is poor and you just have one person representing like an entire demographic, right? So, you know, maybe a company surveys peoples and they have one person who's under the age of 20, all right? That one person is going to be now represent the entire kind of demographic there. It's a silly idea, okay? So I think I've summarized a lot of those comments just on this slide right here. Okay, final warnings. Correlation is not causation. We've gone over this a few times already today. Just because there is a trend or relationship association between two variables doesn't necessarily mean that one thing is causing the other, okay? Or that the other is causing one. There could be all kinds of other things, complicated things going on. So just be careful there, okay? Another one, don't extrapolate. Extrapolate is trying to make predictions beyond where you've collected data, okay? An example of silly extrapolation would be, let's say you have a child and you decide to measure this child's height, okay? You're taking measurements on a child. From age 2 to age 12, you measure this person's height. Every single year, this person is getting taller. Age 2, they're this tall. Age 3, they're a little taller. Age 4, they're taller. Age 5, they're taller. Age 6, they're taller. Age 7, they're taller. They get taller every single year. And this trend has carried on for the last 10 years. Okay? And so you say, well, if this trend continues, by the time this person reaches age 70, they're going to be 18 feet tall. Okay? And we know that's silly, right? Because we know we know people grow and they keep growing, maybe, you know, somewhere until they're what, 16 to 20 years old. That's when people kind of stop growing. And then they kind of remain that height for the rest of their life or until maybe old age where they start to, you know, shrink or whatever. So we know that's silly, okay? But you can imagine anyone taking any kind of trend line and then just projecting it 20 years, 30 years, 40 years into the future. They could say this trend has existed every year for the past 10 years or past 20 years or past 30 years. And therefore, 30 years into the future, we're going to predict this. 50 years into the future, we predict this. And maybe, but maybe not, okay? We don't know if this linear trend, this linear relationship will continue well into the future. It could rapidly increase and go faster. It could level off and slow. It could actually reverse too. There's all kinds of things that could happen. And we don't know, right? So sometimes things grow exponentially. Things have been growing linearly, and then after a certain point, they actually get faster and faster and faster, right? Or they could continue on a linear trend. They could slow down and level off. They could slow down and reverse and actually come down, okay? Depends on a bunch of different factors. And so just assuming something is linear, not a good idea. Okay, the last thing is what we call the coefficient of determination. That's the R-squared value. Basically, for linear regression, you take the correlation R, and if you square it, you get your R-squared value, okay? So because R is always between -1 and +1, when you do R squared, you're always going to get a positive value between 0 and 1, okay? And it's kind of this idea of how much variation in the response is explained by the variation in X. A loose, you know, I hesitate to use this because it's not exactly right, but you could kind of think of like, all right, let's see if we could predict someone's height. Okay, let's see if we could predict someone's height based on, or let's see if we could predict someone's weight. Okay, let's see if we could predict someone's weight. Now, someone's weight is determined by all kinds of factors. Things like their own genetics, their diet, and, you know, maybe their height plays a role into it, okay? And so you can kind of think of all of these different factors that play a role into what ultimately determines somebody's weight, okay? Well, how much can we assign to height? All right, if you look at the correlation between height and weight, you might be able to assign a certain percentage of that to height, and that's kind of loosely one way to think about R squared. It's technically not the formal definition, but if you just kind of have this tough idea of how much variation in the response is explained by the explanatory variable, that's a loose way to think about it, okay? Basically, larger R squared values mean a stronger relationship. So R squared is a 0.9. Those are really strong relationships. Whereas R squared of like 0.1 indicates, you know, not a very strong relationship between X and Y. All right, let me give you your last view quiz answer. Today's last view quiz answer is E. E as in elephant. E as in elephant. And I guess we'll finish just a little bit early today. So so that wraps up for today's lecture. And yeah, so we'll see you on Wednesday. Make sure you, well, I hope your lab is going well. And if you have any questions or anything like that, I've got office hours. I did make some adjustments in office hours. So office hours, I think, will now go from 11:30 to 1 o'clock. 11:30 to 1 o'clock, and also by appointment too. So that wraps it up for today. We'll see you guys on Wednesday. Have a good rest of your day.